Okay, good afternoon, everyone. My name is Charles Jie. I'm a professor from University of Toronto, not very far from here, about 900 kilometers away. It's my great pleasure to introduce our keynote speaker, Peter Bauer from University of Notre Dame. Peter Bauer from electrical engineering. So Peter, please.
For the nice introduction. I'd like to also thank MIT and the organizers of the conference, and especially Ray Rui for inviting me for giving this presentation. I think conferences like that on sustainability are very important because what we do now in sustainability will affect the fate of the planet and our children and their descendants. So what could be more important than that? Let's go straight to the outline of the presentation. In the introduction, I'd like to give you a little bit more of motivation, and I'd like to introduce three arising concepts, namely e-drives, autonomous driving, and networked vehicles, and show you what opportunity those three concepts together provide. Then I'll go through 5 different topics, all of which are very much related to these 3 concepts. Topic 1 is basically the model that you need. You need to have an analytical model to do anything in terms of optimization. But I'd spare you most of the equations. I'll just go through the basics there. Then I'd go through the electric transportation energy sensitivity. That's explaining many of the things that I'll present later. After that, sustainable driving, that requires autonomy also, and I'll kind of show you the key elements of that. Topic 4 is the topic I'm currently working on with my graduate students. It's energy optimal speed profiles. This has the biggest potential for savings, in my personal opinion. I'll spend a significant amount of time on that. Finally, if time permits, optimal stochastic eco-routing and conclusions and required work for the topic of the conference, that plan A plus B. So let's get started with the introduction. You all know that electric vehicles have a number of benefits, and one of them is, of course, their high efficiency if you go from the energy source in the vehicle to the power at the wheel. So for conventional gasoline vehicles, actually for electric vehicles it's 62 to 68%, and for conventional gasoline vehicles it's 18 to 25%, but it can be much lower. If you stand in congested traffic, this goes down to the single digit percents. Then of course, we know electric vehicles are environmentally friendly. There are no tailpipe emissions if power comes from a clean source. If it comes from a fossil fuel burning power plant, then this is not the case. Also, there are a lot of performance benefits in electric drives. It's very smooth, it's very direct, there are no delays, and of course, it's pretty much maintenance-free. So these are all advantages. And also in the US, a lot of times, the reduction on energy dependency is quite an issue. I'd like to mention 2 new concepts that are on the horizon that are very important and make up the fundamental premise of this talk. One is the advent of self-driving systems. In order to execute optimal or energy optimal algorithms, you have to have a computer running your car, because a human A can't do it, and B most likely is not willing to do it. And also, if you have self-driving software, you usually have a pretty high-powered processor in there that can do real-time optimization and executing the algorithm. Third component is global traffic situational awareness. Right now, you hear a lot of networked vehicles and the situational awareness concepts that are popping up everywhere. This is very important to plan ahead and incorporate situations like traffic jams, weather and environmental information. So these three together, self-driving systems, global situational awareness, and e-drives, that I'll show you will bring about many, many opportunities for sustainability in transportation. So this is how I see the whole picture. Electric drives together with intelligent transportation systems and autonomous driving put together, that provides you a sustainable transportation system. But in order to exploit that, you need to have a good model for estimation and prediction of energy usage in a vehicle. And when you have that, you can do many things with it. Today, I'll be concentrating on this side, optimal energy utilization for electric vehicles, optimal speed profiles, eco-routing strategies, but you can also do things like sustainable strategies for energy management, where to place your charging stations, and things like that. So that gets us to topic one, the model. I don't want to spend too much time on it, but you should know that the battery is basically the primary source of electric vehicles. By the way, this entire talk is on electric drivetrains. What I'm going to show you does not work very well for conventional gasoline vehicles. And the power flow is from the battery to the wheels, and it goes through all these components like the power converter, motor controller, electric motor, mechanical powertrain, and each of these components have an efficiency connected with it. And you also have a reverse power flow for regenerative braking, and you have different efficiencies associated with it. Very particular in electric drives is that that parasitic power comes from the battery directly. So if you have your heater on or your air condition, that directly affects your range, for example. If you look at the power needs at the wheel, it has three main components. One is to overcome air drag. The other one is to overcome rolling resistance. And the other one is to overcome the force to overcome acceleration. There is a fourth one, it's hill climbing. We set it for simplicity to 0 in this particular case. So in equations, again, the same thing. The power coming out of the battery minus the parasitic power goes through the cascade of these different components. So you multiply all these efficiencies. What comes out on the right side is the power that arrives at the wheel. That power splits up in air drag, rolling resistance power, hill climbing, and acceleration power. So now you can do different things with it. On the left in red, here you see trip-level energy cost minimization. This is what we are interested in this talk, mostly. So with the route information, traffic information, and the environmental profile, and the vehicle data, you can do trip-level energy optimization and minimization. But you can do other things. You can, in blue, basically find the reachable range and optimize that. So for that, you need starting location, energy cost constraints, the routing engine, traffic information, and environmental profile. If you compare this with a regular trip computer, it tells you, well, you have 30 more miles or you have 50 more miles. For electric vehicles, this is often not good enough, and you need to have a reachable range or reachable destinations on a map, because due to the high sensitivity of electric drives, I'll comment on that in a second, these regions are not, these regions are not concentric circles, and they are not even scaling with energy. So that gets me to topic 2, which is very fundamental for this talk. It's transportation energy sensitivity. Electric drives have a much higher sensitivity to environmental or external effects. And for example, wind speed, dynamic coefficient of rolling resistance, parasitic power, and temperature all affect the range and the power needs of an electric vehicle. And what in the first part of the talk I am going to suggest is that we can exploit these environmental factors. The sensitivities for conventional ICEs, this is always the question I get at this point, is Yeah, so you can do this for electric vehicles, but you can't do it for conventional vehicles. Why is that? And the reason for that is it lies in the characteristic of the efficiency curves in the torque versus speed diagram. In electric vehicles, you have a large plateau that then falls down towards t equals 0 and omega equals 0. For ICEs, it's a very pronounced optimum in the middle. So when, for example, you get a headwind and you have to overcome that additional resistance with a higher torque, what happens is a gasoline vehicle moves into a more efficient operating point, masking the effect of additional power, and you don't see that very much. Whereas in an electric vehicle, efficiency is about the same. So you need 50% more power, you draw 50% more power from the battery. So that's the difference. And this, at the same time, provides opportunities for efficiency optimization. It's very well known in the past that depending on where you run your electric vehicle in the United States geographically, it takes more or less power in the warm areas and flat areas. You're doing much better than in the hilly and cold areas. And so I give you a bunch of examples and simulation results that show you the different sensitivities. We define sensitivity as everybody. It's basically the effect of a relative change in the quantity x on the effect of the relative change of a quantity p. X, in our case, is rolling resistance, wind speed, things like that, and p is the battery power. So here are two examples to illustrate the point. In both examples, we are looking at a Model S Tesla. Temperature is the same, 68 Fahrenheit. Rolling resistance is the same, 0.01, that's typical. But on the left side, we are doing highway driving at 60 miles an hour. On the right side, we are doing city driving at 40 miles an hour. On the left side, we have a headwind of 30 miles an hour. On the right side, a headwind of 10 miles an hour. In big cities, you don't get lots of wind typically, and because it's occluded by buildings. So if you look at this, in the highway driving, the wind speed sensitivity is huge compared to the city driving. Rolling resistance, on the other hand, is not such a big factor, but in city driving, it makes up quite a bit. Parasitic power almost plays no role in highway driving because most of the power goes to propulsion, whereas in city driving, this is an important factor. Temperature effects are about the same. So let me show you the sensitivity via a energy analysis of a very particular drive, namely from Notre Dame to Chicago along I-80, I-90 with 5 different vehicles: Tesla Model S, Nissan Leaf, Honda Fit, Fiat 500e, and BMW i3. Data is here. And what I show you is the energy requirement to do this trip as a function of each of these environmental variables. So, for example, here to the right you have wind speed. Here you have energy consumption for the entire trip, considering all components. So if the wind blows from the north or the south, you don't see much of a dependency because it's orthogonal to the direction of the vehicle. If the wind comes from the west, you see a steep dependency. You go in the Tesla from 30 kilowatt hours to about 40 kilowatt hours by adding a headwind of 20 miles an hour. If it's a tailwind, the opposite is true. The Tesla would go from 30 to about 22 if you have a tailwind. Similar drastic results are true for the rolling resistance. If you look again at the 5 vehicles, the blue one is the Tesla. It's a little bit of an outlier because of the higher weight. The others are about in the same weight class. So you see that if the rolling resistance on a clear highway on a sunny day, it's typically 0.01, and you change that to a snowy road that has slush on it, it's typically between 0.02 and 0.025. You see that that trip energy changes from 30 to about 40, 45 here. So you see a huge change in the energy demand for this trip on an electric vehicle. The gasoline vehicle, you see it a little bit, but you don't see it like this. So the similar situation appears to be the case with temperature. The dependency is not as great. But the warmer the temperature, the higher the efficiency of the battery, and all vehicles perform about the same. And for the energy consumption as a function of the parasitic power, there's almost no dependency. Why? Because when you go with 70 miles an hour on I-80, you're burning about 30 kilowatts for transportation energy. And whether you have a AC unit on at 100 or 500 watts, it doesn't really matter much in the big picture. All right, that gets me to the next topic. Topic 3, sustainable autonomous driving. So now you can exploit exactly these dependencies to minimize energy. And what we'll be doing here is I'll be showing you, or I'll be concentrating on the effect of the wind speed. You can, of course, let me go back. All right. You can, of course, combine all these four and the effects of these four, but I'm just kind of going through the effect of the wind speed. Otherwise, it would be too much for this talk. On the right side here, you see the effect of the wind speed in different colors. So that's the range of a Tesla Model S with the 10 kilowatt hour energy reserve. And you see how it changes as a function of the wind blowing from different directions. Red is the nominal case where you basically have no wind. The same thing here for the different coefficients of rolling resistance. You again see how the reachable ranges change if you start in South Bend, Indiana, here in the center. It is very well known that the range of an electric vehicle has an exact maximum as a function of speed. And this comes from the fact that you have parasitic power. So if you go very, very slow, it's not true that you go the furthest, even though your transportation power is the lowest, but you would take a long time to cover a certain distance, so you burn most of the power in parasitic power, like heating and so on. So there's a very pronounced maximum here. This is important if you want to do optimization. If you want to do optimization, and I don't want to kind of bore you too much with the equations, but you have to get the typical speed profiles, which are given as v of t as a function of time, into v of s, a function of distance, because then you can just simply integrate f of s ds, which is work at the wheel, force ds, and then you go 1 over eta, that's the efficiency of the entire driveline, and then you arrive at the energy expended at the battery. So if you do this, you can formulate two optimization problems. One is minimum energy cost with a time constraint, and the other one is the dual problem, minimum time cost with an energy constraint. This is the typical one that people want. You want to minimize transportation energy given a certain arrival time. That happens in most of the cases. There are some situations where you want to minimize time cost with a energy constraint. Think about electric vehicle racing, for example. What would be that? You want to minimize time given what you have in your batteries, so to speak. Analytically, basically the cost function is just FDS divided by 1 over eta, the efficiency. This gives you the energy expenditure at the battery. On the other side, the total time is ds over v of s integrated, because ds over v of s is dt, so you're integrating dt from the beginning to the end. And these are the typical constraints in between, minimum, maximum speed, and here you have the time constraint, and here you have the energy constraint. Let me show you in form of an example that this is really relevant and it makes a difference. So let's say you're driving a truck, a 10-ton truck with 8 square meters frontal area, and you're driving that from A to B, and you have two routes. The first route, R1, encounters on the vertical part a headwind of 10 meters per second, and then in the horizontal part, it has variable wind speeds that it encounters, frontal and wind from the back. Whereas on the other route, R2, you also have on the horizontal part these varying wind speeds. between minus and plus 10 meters per second. But then on the second part here, you have only a tailwind. If you do the simulation, you'll see that route 1 costs you 3,989 kilowatt hours, route 2, 2,485. That's a saving of 37.7%. If you do that with a diesel truck, you don't even see 10%. So this is a very pronounced phenomenon that people who actually drive electric cars will be telling you that it's very sensitive to these effects. A little word on how to do that optimization with respect to wind speed on the horizontal parts. On the horizontal parts, we assume that the wind speed shown here is changing between minus and 10 plus 10 meters per second. So now what you do is you adapt the vehicle speed to that. So if you have a strong headwind, you slow down. If you have a strong tailwind, you accelerate. And by adapting this, you can actually eke out quite a percentage gain in efficiency. All right, that gets me to topic 4. This is something we are actively working on right now, and I think this has the most promise. The example I showed you before has a savings of 37%. It was a little bit optimistic because I assumed 20 miles per hour winds. That's pretty strong. You don't have that all the time, so 37% is quite high. It's probably more 15 to 25% under windy situations that you'll see in reality. What I'll talk to you about here is optimal stop-to-stop speed trajectories in cities. If you think about city traffic, it's always stop-to-stop. Even if you have a green wave, eventually you'll come to a stop. And with all the debate on emissions in cities, especially the diesel debate going on in Europe right now, it's understandable that, especially in cities, you want to minimize energy usage, minimize tailpipe emissions, et cetera, et cetera. So here, I posed 3 questions. Given the average speed between 2 stops, or 2 speed constraints in general, what is the energy optimal speed trajectory? So there are infinitely many trajectories that get you from A to B at the same time, the same time cost. But there's only one that minimizes the energy consumption. How much transportation energy can be saved with that, with the optimal one? And what about realizability? So this can be formulated as a constraint optimization problem, as I showed you before, where the cost function is only transportation energy. Some of my colleagues have done this before as a mixed optimization. You won't get even close to the gains that I'll show you here. It has to be, the cost function has to be only transportation energy, and all other conditions have to go into the constraints. So the blue curve is a typical stop-to-stop curve in city traffic. It actually comes from a distilled FTP75 drive cycle. The red one, or orange one, is the optimized one. You see this here is speed versus time, this here is power versus time, and this is cumulative energy at the battery over time. You see what the optimal does. It spends a lot of power at the beginning, energy at the beginning, and ramps up here, but then it coasts, and then it has regenerative braking, and you recover some of the energy here. You see there's a difference of about 40–50% in terms of energy recovery. Also see what the optimizer does. The blue trajectory is the regular one. This is in the regen area, that's forward. And this is the optimal one. The optimal one tries to put the trajectory into the high plateau of energy efficiency of electric drives. And therefore you save a lot of energy. There's a second example. So this was a Nissan Leaf for 400 meters, 10 meters per second average speed. So that's 40 seconds total trip time. If you go to this example, that's 100 seconds trip time, also at 10 meters per second average speed. You see what the optimizer does. It does not want to go at a constant speed here, because at a constant speed at 10 meters per second, you would be in the bad efficiency areas that are shown in kind of blue or yellow here. So what it does is it accelerates hard, it coasts. It accelerates, it coasts. It accelerates hard, it coasts. To always put the operating point in the high efficiency regime. With that, you will, again, get 50% energy savings with that, which is actually huge. And imagine a 50% energy savings in city driving translates into a doubling of the range, of the reach of the vehicle, roughly, because there's parasitic power, so it's not exactly true. So here we put a table together for two vehicles, the Tesla Model S and the Nissan Leaf, two different speeds, 10 and 18 meters per second, two different segment lengths. So now you see how the infrastructure, segment lengths and speed, affect basically the energy savings. And you see they are consistently in the 40 to 50% range. Only the Nissan Leaf at 300 meters is down at 26. Actually, one particular thing we observed, which is absolutely not true for conventional vehicles, is the more acceleration power you have, the more you can save. So this is counterintuitive compared to gasoline or diesel vehicles. In general, as a summary of the results for topic 4, it turns out that vehicle parameters like mass, air drag, rolling resistance are not that important. It doesn't really change too much the optimal trajectory. What's important is the distance segment length, the efficiency map of the drivetrain, and basically the environmental conditions. And also powerful vehicles have an advantage. Of course, the problems to overcome are jerk. In an autonomously driving vehicle, if this thing takes off with 8 meters per second squared without a warning, you're going to wear your cappuccino in the car because you couldn't expect it, right? So you have to have a method to kind of ramp this up somehow or give a warning or something like that. Or you reduce the acceleration, then you get some penalty on the savings. Two afterthoughts to this. These are the optimal trajectories for 5 different vehicles, same infrastructural constraints, same arrival time, same distance. And except for this one outlier here, which is an artificial vehicle, it's not a real vehicle, that's what we call a lossy vehicle. Huge CDA product and very little mass. So it's kind of very little recoverable energy through regenerative braking. Except for this one, all the others look very, very similar. All the optimal trajectories come in very close. What does that mean? What are the implications of that for urban driving? This is what it means. It means platooning in urban situations makes sense. Because then you have a lead vehicle that has all that software, it has self-driving, etc. And all the following vehicles only need to have like level 2 or level 3 self-driving, and you can save a lot of energy. So this is the kind of stuff we are working on right now. I don't want to get further into that. This leads me to topic 5. So in topic 5, we looked at stochastic optimal echo routing. And the problem is this. You want to go from a starting location S to a destination D, but you have many different routes you can take. Each vertex is labeled with an energy cost. This energy cost is stochastic. It turns out if it's distributed in a Gaussian, then there are some really nice ways to solve this problem analytically. Unfortunately, in reality, it's not Gaussian. What you do here is you minimize the expected value of the sum of the energy along a particular route, and you are having as a constraint that you reach your goal. That's basically an energy constraint. You have eta in your battery, so to speak, and the route costs you the sum of Eij, Xij, and you want to satisfy this with probability P. This is just a connectivity constraint on the graph. And if you do this, you can actually do optimization of long trips or city driving. If you do this in city driving, the So this is a city of 10 times 10 blocks. And what the surprising outcome is that different wind profiles, different vehicles, and different regen efficiencies lead to different trajectories through the city. In terms of the distance cost, they're all the same because you're going diagonally from down there to up here, unless you reverse the direction. But if you always go forward to the goal, the distance cost is always the same. But with these different environmental conditions, the optimum path always changes. You can argue in city driving, this doesn't make too much of a difference, which is true because you won't have on one block, you will have snow, and in the other one, you'll have sunshine and it's a clear road. That won't happen. So it's very uniform. Wind also is probably pretty uniform. But where it is important and makes a difference is long distance trips, like this trip from Chicago to Miami. I'd like to kind of come to the conclusion and like to reinforce that there are three concepts that are the key to what I think will be a revolution in sustainable transportation. And they come from the energy-aware optimal e-driving strategies. So you need an electric drive, but you need to also have situational awareness to kind of make the whole thing happening. So this is the networked vehicle concept where you now can communicate data on what's coming, so to speak. But communicating wind speed half a mile down is very difficult, or communicating other weather kind of situations. Waze already does things like there's a traffic accident there or there's a congestion here, but to communicate environmental conditions, it's difficult. So some of the stuff you can do now under plan A, so to speak, because we have some traffic situational awareness, we have electric drives, and we have some level of autonomous driving. So it's right now is the time to kind of get this started. Of course, the end game would be global situational awareness and application of energy-aware optimal e-driving strategies in every vehicle or almost every vehicle, and then you get global sustainable transportation. So what are the showstoppers so far? A few things that are missing are the handling of unforeseen situations. So you cannot always predict what happens half a mile down the road. Even though you have sensors and you have situational awareness, there may be this dog that is crossing that nobody knows about, and then you have your tricycle and goes down the drain, and you have to brake, and you have to kind of recompute everything. And the other thing is real-time optimization. So it takes a lot of computational power to do this from stop to stop. But there are ways around that. And finally, I'd like to say what you can do in the meanwhile is have interim solutions on dedicated lanes and urban platoons, maybe in fleets, in city vehicles like city buses, and this way get the entire process started. Well, this concludes my talk. I'd like to thank especially Eduardo Mello and Songen Yi, who both did their PhD with me, and I drew stuff with their permission from their thesis. And yeah, I'd like to open it up for questions.
Marvelous talk. We have time for questions. One of the findings to me is very surprising that they said that more powerful vehicles have advantage. For example, you use Tesla S, right, compared to a Nissan Leaf.
Right.
But on the other hand, that Tesla S is much more heavier, right? So in the sense that you carry, you down, right? So what is the reason for that?
Yeah, it's only the relative saving of the Tesla S with respect to the regular driving profile.
Okay, percentage of
yes, percentage savings.
So Tesla is still more expensive.
Yes.
But let's say hypothetically I have a same vehicle, okay?
Right.
Same weight,
right.
But one with bigger battery power, okay? So more powerful, but yet have the same drag.
Yeah, if everything is the same, the mass is the same, drag is the same.
So which one will have advantage?
The one with the higher power.
Okay. Very surprising.
Yes.
Okay. Actually, fascinating talk. I have another question here. So that you have that regenerative braking, right?
Right.
My understanding that in order to achieve that, you actually have a capacitor, let's say, in series with battery. I don't know if you know the details of what is energy, proportional energy actually can be absorbed by the question that how important actually the capacitor is to the energy performance.
So if you look at these performance curves and deceleration rates, they are fairly high. So if you compare compute the MVA, the regen power sometimes reaches pretty high values. And for that, it's very advantageous to have a hybridized power source. That means battery plus ultracapacitors, and then out into the cascade of components. So the ultracapacitors could take up 100, 200 kilowatts in terms of regen power, which is a problem for batteries sometimes to kind of pump that much power into batteries. So depending on the size of the battery.
Make lots of sense. I have lots of questions, but I like to actually invite people here. Anybody drive an electric car? Nobody? It's very popular in California, but in your place here it's not as popular in California. Questions? If not, let's thank our speakers.
Thank you.
So we have a little bit, just a little bit. Actually, okay, I'm not saying you should, that's okay.